66 stars and constellations, divided into 3 celestial roads belonging to the gods Enlil, Anu, and Ea, are all catalogued on clay tablets copied around 687 BC. But when astronomers tested nearly 190 of its recorded observations against statistical models, the best fit date was not the 7th century. It was 1370 BC. Something far older is embedded in these tablets. In the vaults of the British Museum, 6 clay tablets catalogued as BM 33102 through 33107 form the most complete record of MUL.APIN, recovered from the Royal Library of Ashurbanipal at Nineveh. These tablets, excavated during early 20th century campaigns at Kuyunjik, bear the marks of a careful, institutional chain of custody. Each measures around 15 by 7 centimeters, inscribed with dense, cuneiform columns that preserve the astronomical compendium in remarkable detail. Alongside the Nineveh series, a single copy from Assur stands out. Its colophon, copied by the priest-scholar MUL.APIN in 687 BC, names the year and the reigning king, Ashur-zur-E, anchoring the MUL.APIN tradition at least a century before the fall of Nineveh. Today, this Assur tablet resides in the Louvre under inventory AO 1975-45, its journey documented through museum records and legal export permits. Beyond these core exemplars, scholars have traced between 40 and 60 additional fragments, some no larger than a coin, across collections in London, Berlin, Paris, Baghdad, and university archives. Each fragment, catalogued and digitized by the Cuneiform Digital Library Initiative, attests to a long tradition of copying and recopying. None of the surviving tablets is an original autograph. Each is a witness to centuries of transmission, correction, and preservation. The text itself spans 2 principal tablets, with later sources hinting at a 3rd auxiliary volume that remains lost. Together, these manuscripts form a dispersed but interconnected corpus, offering a direct material link from the hands of ancient scribes to the present, and setting the stage for the analysis of the tablet's internal astronomical schema. The MUL.APIN tablets lay out the sky as a tripartite map, dividing the heavens into 3 broad bands, each ruled by a different god. The northernmost path belongs to Enlil, stretching from the horizon up to about 17 degrees north of the celestial equator. Within this domain, scribes counted 33 distinct stars and constellations. The central band, the path of Anu, runs along the celestial equator itself, bounded by the same limits of 17 degrees north and south. Here, 23 named asterisms are catalogued. To the south, the path of Ea extends down from 17 degrees south of the equator toward the unseen depths, containing 15 constellations. These boundaries are not arbitrary. They reflect careful observation, an attempt to capture the sky's structure in terms of latitude, using the declination of stars as a practical dividing line. The sun itself travels through each of these paths for roughly 3 months each year, marking the seasons. This tripartite division transforms the night sky into a celestial map, where every visible star is assigned its place, and each region is under the patronage of a different deity. The result is both a functional calendar and a cosmic order, setting the stage for the detailed star names and constellations that follow. Anchoring the abstract scheme of MUL.APIN to the night sky begins with a handful of unmistakable star groups, each named and positioned with a precision that still resonates. The Plough, known today as Ursa Major or the Big Dipper, stands at the head of Enlil's path. Its 7 stars, easily visible from Mesopotamia, served as a reliable guide for orientation and timekeeping. Nearby, the Great Twins, mapped to the constellation Gemini, signaled the changing of seasons, their dual form echoing through both cuneiform lists and later Greek tradition. The Great Square, identified as Pegasus, marks the heart of Anu's equatorial band. Its 4 bright corners form a striking geometric figure used by Babylonian scribes to partition the sky and track the moon's passage. Among individual stars, Regulus, the king's star, holds a central place. Named Su-an-Na in the tablets, Regulus is the brightest star in Leo and was singled out as a royal marker, its heliacal rising closely followed for calendrical and ritual purposes. The compendium also records the 5 visible planets: Mercury, Venus, Mars, Jupiter, and Saturn. Each assigned a place in the 3 roads, their wandering paths carefully distinguished from the fixed stars. These anchors, identified through modern philology and precessional calculations, lock the ancient system to real points in the sky. With these names and forms, the MUL.APIN catalog transforms from abstract schema to a functional map, preparing the ground for the operational tables that follow. The internal logic of MUL.APIN comes alive through a series of operational tables, each designed to turn raw observation into practical knowledge. The most prominent is the heliacal rising calendar, a list that assigns 34 specific stars to fixed months, tracking the moment each first becomes visible in the dawn sky after its annual disappearance. This table forms the backbone of the Babylonian seasonal year, with the plough's appearance in Sivan marking the start of agricultural labor. Alongside it, the paired rise and set list matches the rising of one star with the setting of another on the opposite horizon. For example, the simultaneous appearance of Sirius and the disappearance of Orion served as a nighttime clock, allowing scribes to check their calculations against the real sky. A separate interval table records the number of days between the risings of key stars, providing a self-correcting system that could compensate for cloudy nights or errors in observation. The Ziqpa'u, or hour-marking stars, divide the night into regular intervals, 12 in total, each linked to a specific asterism. This proto-timekeeping system allowed priests and astronomers to synchronize rituals and measurements long before mechanical clocks. Finally, the lunar path list traces the moon's monthly journey through a sequence of asterisms, laying the groundwork for the later zodiac. Each of these lists encodes not only the positions of stars, but also a method for predicting, measuring, and verifying celestial events. Together, they reveal a toolkit that is both empirical and systematic, grounding Babylonian astronomy in observation and calculation, rather than myth alone. MUL.APIN's star catalog marks a turning point in the ancient world, not just for its structure, but for the accuracy woven into its records. Babylonian scribes mapped the heavens into 3 divine bands: Enlil's north, Anu's equator, and Ea's south, assigning each asterism a fixed place. 33 asterisms line Enlil's path, 23 fill Anu's, and 15 belong to Ea. Heliacal rising dates for 34 stars, calculated for Nineveh's latitude, match modern astronomy within 2 or 3 days. That level of precision was unmatched until the Greeks, and in Egypt, only Sirius comes close. Egypt's decanal lists, by contrast, organized the night sky into star groups that rose every 10 days, shaping ritual calendars but never mapping every visible star to a specific zone. Greek astronomy, centuries later, produced systematic catalogues and the zodiac, yet the earliest Greek records from Hipparchus and Ptolemy appear 5 centuries after MUL.APIN's oldest copies. Early Chinese astronomy, with the Shishen star list, shows similar cataloging efforts, but no evidence of a 3-path division or of a rising calendar precise to the month. Transmission studies reveal how MUL.APIN's star names and groupings entered the Hellenistic world. Berossus preserved 7 asterisms, and Babylonian tables were translated in Alexandria and Antioch. Still, MUL.APIN's comprehensive mapping and operational tables remain unmatched, challenging assumptions about the origins of scientific astronomy. Dating the MUL.APIN compendium has become a test case for how far modern methods can penetrate the past. Statistical analysis, using chi-square fits of heliacal rising dates against astronomical models, points to a best-fit epoch near 1370 BC, with a margin of error of around a century. This result is reinforced by independent modeling, which clusters the observations between 1400 and 1100 BC. Attempts to push the origins back to 2300 BC, popular in early 20th century scholarship, now fail under closer scrutiny because the statistical fit for that era is poor, and the linguistic evidence does not support such antiquity. But the tablets themselves are products of a much later world. The Assur copy, explicitly dated to 687 BC, and the Nineveh series, written in the 7th century, both reflect a tradition of copying and redaction. Stylistic analysis reveals layers within the text. Simple star lists coexist with more complex paired rise tables, suggesting editorial accretion over centuries. Shifts in sign usage, such as the transition from the MUL logogram to KUR, hint at evolving scribal conventions. The result is a palimpsest, where the precision of the astronomical data anchors the text in the late Bronze Age, but the composition bears the marks of a long, multi-generational editorial process. These converging lines of evidence, statistical, philological, and paleographic, force a reckoning with the depth of Babylonian skywatching, and with the limits of what can be known about its earliest roots. Venus stands at the heart of MUL's technical achievement. The compendium's record of the planet's 8-year cycle, 5 synodic periods matching almost exactly 2,920 days, deviates from modern calculations by no more than a single day. This level of precision, reached more than a millennium before Greek astronomy formalized planetary theory, continues to puzzle researchers. Ecliptic longitudes for the 33 stars of Enlil's path, when adjusted for precession to the late Bronze Age, fall within 5 to 10 degrees of their actual positions. These are not isolated cases. Across the heliacal rising tables, star after star appears in the correct month, the error rarely exceeding 3 days. Yet the numbers only tell part of the story. In recent years, micro-computed tomography imaging has exposed erased signs and marginal corrections on battered tablets, revealing a process of continuous refinement. Machine learning models, trained on thousands of cuneiform fragments, have stitched together lines once thought lost, extending the known text and confirming the Venus cycle's accuracy. Artificial intelligence-driven fragment matching has even proposed new joins between pieces in Berlin and London, hinting at a larger, more complete compendium still buried in museum basements. For every benchmark met by MUL.APIN, new questions surface. How did ancient observers achieve such accuracy without optical aids? Did they inherit generations of cumulative records? Or did a single epoch of careful sky watching set the standard? As technology pulls more detail from clay and dust, The boundaries between observation, tradition, and scholarly invention remain unresolved. Each advance brings the ancient sky watchers into sharper focus and leaves the origins of their knowledge as mysterious as ever. Today, MUL.APIN stands as both artifact and anomaly, a star catalogue whose precision still unsettles scholars. As astronomical modeling pushes its data further back than its tablets, the true origins remain elusive. The question persists: how much ancient knowledge have we underestimated, waiting in lines of cuneiform?